Okay, sorry, last clip I just got cut off there. I pushed the wrong button. I meant to pause the computer, but what happened was instead of pausing it, I guess I actually exited out. But anyway, we were going to do this problem, and for this problem, let's consider a bicycle here going around a circle of radius 2 meters. This is not a very big circle. And the rider of the bike plus the bike have a combined mass of 43 kilograms. And their tangential velocity, which is the velocity that they're going around the circle with, that's the tangential velocity, v sub t, is 2 meters per second. And I'm going to ask you to calculate the centripetal acceleration. So can you do that? A sub c is the tangential velocity squared divided by the radius. So you take the tangential velocity, which is 2. We're going to square that, and we're going to divide by the radius, which is 2. And if we do that, we find that the centripetal acceleration is 2 meters per second squared, because that's the SI units for acceleration. Okay, now suppose I wanted to know what the centripetal force was. Well, the centripetal force is just the mass multiplied by or times the centripetal acceleration. So the mass of the object, 43 kilograms, that's the bike plus the rider. The acceleration we just calculated up here, so we're going to plug that in. That's 2. And we see that the force would be 86 newtons. So what kind of force provides the centripetal acceleration? What's providing the centripetal force inward? Remember, the centripetal force is always inward and in the direction of the acceleration, which is always in towards the center. Well, it's going to be the friction. So friction of the tires with the road is providing this centripetal force. Now, same thing with a car. When you're in a car, it's the friction of the tires with the road that is providing this centripetal acceleration towards the center. So if we had a car, here's our road, and it's getting very difficult here to make nice circles, but I kind of think you understand what's going on. The car is going this way. It's about to make a turn, and the car makes a turn, so it's coming up on our turn over here, and something has to be providing our centripetal acceleration, again, always directed towards the center, and our centripetal force, again, always directed towards the center in the same direction as the acceleration. Something's providing that. What is it providing that? It's friction of the tires. But now, as the car is going to turn, because it has friction is pulling it in this direction towards the center, what happens to you as you're sitting here in your car? Well, you are going to go out that way because you have something called inertia. And inertia is going to want to keep you going straight. Here you are here, and you're going in this direction straight. All of a sudden the car turns, but you want to keep going straight. So when the car turns and you keep going straight, you're going to go up against the door. So it's inertia that's causing that to happen. Same thing with a ball on a string. You've got tension in the string, and that's going to provide the centripetal force as the ball is going in a circular path. But now if the string breaks, let's break the string, the ball is going to fly off in the same direction as the tangential velocity, because it's going to want to keep on going straight. That's also inertia. Sorry about this. Inertia. It's also inertia that keeps the ball going in a straight path if the rope suddenly breaks. Okay? So those are important concepts that we worked on that we needed to know and understand very well. We talked about gravity, we talked about weight, and we said that, get a little piece over here, we said that in outer space, in fact, on a moon, Here's the moon. Moon. Here's Earth. Much bigger than the moon, right? So here you have Earth. So this is the mass of the Earth and the mass of the moon. And if a guy is standing here on Earth, the force of gravity is down, and he weighs a certain amount. His mass, little m, this make this mass of the moon. And now if he's standing on the moon, he still has the same mass, but the force of gravity is less. So why does the astronaut weigh less on the moon? It's because the astronaut has the gravitational field strength is less on the moon's surface than on the Earth's surface. So we have a gravitational field that's around Earth, always directed towards Earth. We have a gravitational field around the moon that's directed towards the center of the moon. Now, you know, a couple of people on the quizzes were saying that there's no gravity on the moon, and that's why it weighs less. But that's not true. There is gravity on the moon. There's gravity between any two objects that have mass. Since the moon has mass and the astronaut has mass, there's a gravitational attraction between the two. We calculate that by saying the force of gravity is this capital G, which is the universal constant of gravitation, times the mass. If we're on the moon, it would be the mass of the moon, times the mass of the little guy over the radius, in this case the radius of the moon, squared. If we're on Earth, then the force of gravity on Earth would be capital G, mass of the Earth times the mass of the little guy over the radius of the Earth squared. This is always the distance from the center of the object to the center of the object. In this case, if we're measuring gravity, it's center to center. I was just running out of time on this video. Let's continue this thought on the next part. Do it on the next video.